So welcome everyone to the 6th lecture. We are halfway through. Well, not yet, but soon. Some announcements for today. So as you all know, the exercise 1 deadline passed yesterday. The grading will be done in a week, and you'll get your scores in your inbox. Yeah, so afterwards you have this session where you kind of get to know why the grading is like this and so on, right, with the tutor. Yeah, on a separate note, there was feedback last time that I was a little too slow. So I'll try to make sure that I'm going fast enough and not too boring, right, on the materials that are not super exciting. All right. So last time what we did was we did attacks on LLMs, and then we started the second part of the lecture, explainability, and we went through some goals and definitions. They are boring, right? So we had some materials afterwards, right, at the end of this section, but I just cut them out, and then because I thought, yeah, maybe, yeah, these are about different types of XAI, but eventually you'll get to all of these in the lecture, so it doesn't matter too much whether we introduced them already last time or not. So let's jump straight into feature attribution. So what is feature attribution? You're given a model, right? A black box model, and you want to know why the model predicts certain output on my test sample, right? So given an input image, model will do something, and then will predict the label cat. Now you're asking why the model predicts cat. And there's one example of explanation you can give, which is to give a score map, or even better, you can also do some thresholding of the score map to kind of tell the user based on which pixels did the model make this prediction of cat, right? So that's one example of feature attribution. You're attributing the prediction to input features. It could be pixels or many other stuff. Yeah, I explained it all here. Yeah. So what kind of features are we talking about? We just mentioned pixels, right? So for every pixel, we can kind of understand what is the contribution to the prediction. I hope there's no window open. So no. Yeah, this is the best possible audio system. Right, so it could be a single pixel contribution. It could be a set of pixels, like a patch, right? So you can also do some sliding window of the patches and see which patch is contributing the most to the prediction of cat. It could be super pixels if you go a bit higher up in the hierarchy. You can also kind of, yeah, super pixel means you're kind of segregating every pixel into kind of semantically related chunks. So for example, you can have this part here, which may be kind of a small part of the semantically meaningful part of the part of the image. And then finally, we have instance mask, which is a close delineate, like precise delineation of the actual object in the scene, like cat, for example. So we have different levels of possible attributions we can make. It doesn't also have to be just input pixels. You can also attribute to more high-level concepts. For example, you can try to extract attributes like cute, 90%, yeah, furry, yellow eyes, 2 years, animal, pet. And then you now ask, given all these features, right, from the model, why do you think this is a cat? And then you can assign these scores like 90%, 40%, 50%, and so on. So that's another example of attribution. When it's a language model, for example, and you're doing some classification of a sentence, you can try to kind of attribute to individual tokens instead of pixels, right? Because that's sort of the most basic kind of building block for text in language models. So now, given these features, what do? You do counterfactual reasoning, right? That's what explanation is all about, as we discussed last time. So what you can ask is you kind of try out some possibility, like different possibility for a certain patch of pixels in the image. and then ask again, do you still think this is a cat? Or you can also ask, what is the score for a cat in this case, to make it more smooth, yeah, instead of a binary decision of cat or not. But now, here comes the question of what do you exactly mean by removing pixels, right? Sometimes you can do like black pixel removal, right? You just remove the pixel values and then fill that in with 0 values in the RGB scale, or you can fill them up with 128 values, gray pixels, right? Or pink pixels maybe, because pink doesn't appear so much in natural images. Or can do in painting. We're going to discuss all these options. But the point here is that, yeah, removal is kind of important, but how to do removal is not super obvious. In the extreme case, you can also just replace by some random other image as well, right? So this is about counterfactual reasoning, right? You can also ask counterfactual reasoning in high level with respect to high level features, like what if noise is added as opposed to like changing a small part of the image, input image. So that corresponds to ImageNet-C, where people add different types of noises like salt and pepper noise, or Gaussian noise, or blurring, motion blur, and so on. What if the weather condition is different? Yeah, that's also part of ImageNet-C. Or people can also ask, what if the texture part of the image is altered as opposed to the content or the shape part of the image? And that kind of question is also asked a lot in computer vision machine learning. So eventually, with all these options, what we care about is the contributions. So we don't really stop at the question of what happens if I delete this particular patch from the image. What we usually care about is, given all possibilities of deleting certain patches in the image, what's the most important patch? Yeah. So when you delete that patch, then that's gonna induce the greatest change in the model output. Yeah, so we are more interested in this kind of ranking kind of question, where we have to rank the possibilities of changes according to the importance the change is going to make. So we call that kind of contribution and attribution, right? So, and then obviously doing this brute force is of course expensive. First of all, yeah, let's say if it's an image, it's usually 224 by 224 times 3, and that's close to 150,000 possible pixels in the input space. Yeah, altering all of these pixels one by one and checking the outputs of the model. It's even worse if you want to consider not just single pixels, but also like possibly different sizes of windows, right? Then it also increases. There is another axis they have to explore. And also there's yet another axis, which is how you change the inputs for respective locations. So this is super, super expensive, and there should be some approximation available. So that's roughly how feature attribution looks like. Now, let's first start with evaluation. What do we call the best feature attribution to start with? What is the eventual goal, right? It's not an easy question to answer, actually. There like several, I would say more than 10 papers have been dedicated to kind of answering this question so far. So to give you kind of some framework for thinking about the problem in XAI, I wish to kind of introduce 3 layers of abstraction in XAI problem in general. So first of all, we have some real-world problem. Yeah. So examples are my model fails for some cases. The other example is I need to persuade customers with that my model is doing the right job. So I need XAI, the score map, to kind of convince the users that my model is good, apart from just the accuracy score. Often these kind of problems are kind of describing the whole pipeline, which consists of several modules, right? And so if there are several modules, it's not super easy to evaluate because there are so many moving factors, moving parts here. And also, it's not super well-defined and quantifiable. For example, like customer satisfaction, it's not super well quantifiable and also depends on the customer and so on. So the real-world problem itself is not super useful for doing evaluation, as opposed to, let's say, accuracy, like classification accuracy evaluation. That kind of measure aligns super well with the real-life needs, right? You need the model to answer uh, well in many of the cases, right? And that's exactly what accuracy is trying to measure. But in this case, in XAI, there are so many different needs, and there, in so many cases, it's not so obvious how to quantify that. So what people do is to identify a subtask, level 2, where they try to come with a kind of common element for all these applications. It's like a unit test, right? So you don't really test the whole system, but you just test a single module, which is kind of common to many other applications. And there, ideally, the module is super well defined and the result is quantifiable. So for example, an example of that is exactly feature attribution and the faithfulness of feature attribution that, that kind of tells you, determine the change in model output when certain features are altered. So you have your XAI model, and your XAI methodology will tell you how much model output will change when you alter the pixel in this way. Or you can also get information like identify the feature in the input that contributes the most to the current prediction. Yeah, that's already kind of the second stage, which is kind of related to the end goal potentially, but not super obviously, right? And that's kind of the main focus of XAI. And then 3 is, yeah, as I said before, doing this in brute force way is, yeah, possible, but very expensive. So typically XAI methodologists try to do this in an efficient way, and that's the main focus. So from level 1 to 2, XAI domain doesn't care too much. They often take this as granted, meaning that, yeah, feature attribution and understanding the feature contribution is an important problem for many downstream applications. They just take it for granted. But my argument is this actually has to be challenged at times. And then there's a second to third level, which is, given the well-defined task, what is an efficient approximation? And then usually the soundness or faithfulness evaluation is focused on kind of measuring the precision of approximation within a kind of reasonable amount of time. So they measure efficiency and soundness together to kind of see the approximation is doing the right job. So I'm talking about XAI in general, which encompasses feature attribution as well as training data attribution, which is going to be the third part of this section. The structure is the same. You have some real-world problem, and then abstraction, and then approximation. Okay. So now coming down to feature attribution, the task again is measure the change in model output when certain features are erased. Erasing a feature will probably have to be defined more precisely. And here the ground truth to compare against is the actual change in the model output when you erase certain features. Yeah. So by doing this kind of evaluation, we are covering among the 6 criteria that we talked about last time, counterfactual, right, because we are changing the input in different ways, and soundness, right, whether the XAI is giving you the right cause for the change, and efficiency. What about the other criteria like selectivity, social and interactiveness of the explanation, end-to-end usefulness? We don't really directly care about that in this lecture, but these are also very important factors. Okay, so I'm talking a lot about doing evaluation right here because a lot of people some years ago have been doing it wrong, and for the understandable reasons. Yeah, so let's take a look at how it's done before. So this is how not to do it. So people used to do qualitative evaluation on the attributions. Yeah. So for example, there is an image, French horn, right? And then took a look at the score map given by the XAI method. And then yeah, it's actually exactly pointing to the French horn right in the image. Compared to, let's say, so this is input gradient and this is class activation map. And then declare that class activation map is doing a better job than input gradient because it looks nicer, right? And also it's potentially pointing to the right location, like better location than the input gradient. They say, we observe that our CAM approach significantly outperforms the backpropagation approach of 23. That's the exact excerpt from the paper. Here's another one. So they even measure how many times the score map is pointing to the right ground truth object in the scene, right? So there's snowmobile here, right? And then say, yeah, look, if you look at this score map, it's actually pointing to that snowmobile, so it's doing the right job. But is it, right? I'm going to tell you the fallacy here later on. So like doing qualitative evaluation itself is not a problem. The main problem, like even if they do quantitative evaluation like this, there's still a problem, which I'm going to talk about next time. I mean, after this slide. So it's basically saying method A is finding the GT ground truth location better than explainability method B. And so A is better than B. So what do you think is the fallacy here? Maybe you can give an answer before I move on to the next slide. Yes?
Maybe the classification maps don't guarantee that this is actually the explanation for how the model does it.
Yeah, exactly, yeah. Yeah.
The gradients we know, like by the definition of the method, that
Exactly, yeah. So gradient is probably doing the right job because it's kind of doing the job that it's told to do, right? Which is kind of understanding how the model reacts to small changes. And yeah, that probably shows what the model is doing internally, and CAM is probably not showing what the model is exactly doing inside. So doing qualitative evaluation does not really tell much about what the model is actually doing. Yeah, we just measure in this case whether the explanation aligns with human intuition. Yeah. But what I'm trying to say here is that good explanation doesn't necessarily mean it aligns with human expectations. So let's say there's an image and there's a class activation map, like the score map, for dog. And then it's pointing to cat. Now there are two possibilities. One is the explainability method is broken. The model is, yeah, of course, supposed to take a look at the dog pixels to make the prediction. And now your explainability method is doing a wrong job here. Or second possibility is that the model is actually exactly looking at the cat pixels. Yeah. And that's a big problem, right? Because then the model is not doing, it's not robust, right? When you have no cat in this image, then it's probably not going to predict dog, right? And XAI method is exactly designed to kind of catch that. And if you criticize XAI method here for kind of pointing to something that's not aligning with human intuition, then we are missing out the whole case where the model is actually wrong, right? So I hope that's clear. So to wrap up, the problem is you have a system, model F, and then you have an input to the model, and you have an output, and there's an explanation, S of fx. What I'm trying to stress here is that explanation should be a function of the black box function of interest, right? So f comes into the input to the explanation. It has to be, right? Because eventually you have to explain the model and not kind of make a random guess based on x and y alone. But if you do qualitative evaluation, what you're doing is you leave out the dependence on the function altogether, because what you're taking a look is is you take a look at the input and potentially the class, and then by taking a look at the score map afterwards, and then determining whether the score map aligns well with X and Y. But doesn't tell you much about the alignment with the model F. Yeah, so for the same reason, kind of pointing to the kind of measuring the precision, the XAI methodology against the ground truth localization is not a good idea, because we know that models do not always rely on the foreground pixels for making predictions. So, any questions so far, or just move on? So we talked about how not to do it. So how to do it now? Remove and predict paradigm. So what do? I'll jump into the algorithm, how we do remove and predict evaluation. So you're now given a score map of the size of the input, right? What score map is actually telling you is a ranking of pixels according to importance for the model prediction. Okay, so the highest scoring pixel here, high scoring feature here, is supposed to be the most important feature for the prediction of the output. So what you can do, what you can expect from this is that if you remove that pixel corresponding to the highest contribution, then you're going to see the greatest drop in model kind of prediction for the current prediction. Yeah. And you can do the same for in descending order of predicted importance according to the score map, right? So you can also do it like progressively. So you remove the most important one, and then the second important, third important, until you don't have any feature left in the image. And along the way, you can check how much the prediction for the original prediction changes, drops, right? So if it drops quickly, then that kind of means you're actually ranking the pixels in the right way, because that's as expected. So this is how it looks like. So there's an image and there's an explanation here, and then you can remove progressively 10%, 30%, all the way up to 100%. In this case, we notice that the removal is defined by filling in the pixels with gray values. We're going to talk about whether that's the right choice later on. But anyways, afterwards, you can quantify the quality of explanation based on this kind of plot, where on the x-axis, you have different number of pixels removed from 0% to 100%. On the y-axis, we have relative accuracy along the way, where it's again the accuracy is measured against the reference point, which is erasing pixels at random, like uniform random from the image. At least your method has to be better than just random erasure of pixels, right? So that's kind of no information baseline. Your performance will still drop, right, when you erase information from the inputs, right? So you're still going to see like drop, but the question is how much better, right? Better drop in, how much quicker drop in accuracy you're going to see compared to this random erasure, right? So we always do kind of division by this random erasure baseline to compute this kind of relative accuracy. So still, better score map will give a quicker drop in performance here, especially with smaller number of pixels erased. And the lower this value is, then your method is much better. So for example, here red and blue curves are giving pretty good drop in performance, right, for the first few pixels. Right, any questions so far? Okay. So now we can talk about the missingness bias, right? How to erase pixels from an image. The problem is, yeah, you can think of black pixels as kind of a nice proxy for no information, but it's not, right? So let's take a look at these cases where you erase certain patches at random with black pixels. So if you do it randomly, you have this kind of image. You can also erase from the most least salient, the lowest scores, right, in the score map. And you have this kind of image. And if you erase the most important pixels, then you're going to have this kind of image. And let's take a look at what the models predict in each case. Of course, the original prediction is flat warm, right? And since we erased the information about flat warm, then we're not going to see so much flat warm prediction. But now we see that in this random case, the model is predicting crossword. Yeah? And that's kind of understandable, right? Because the configuration of black pixels here looks exactly like crossword puzzle, right? So, and then that kind of means instead of just erasing the flat warm information from the scene, it's actually introducing new information that was not there before, right? Which is crossword, jigsaw puzzle in this third case, and cliff dwelling, right? And these are all kind of understandable. And I guess you kind of see the point now that yeah, these black pixels are actually introducing more information. Also the shape, right? Shape of the erasure, it's giving a lot of information about um, the yeah, about the black pixels. So it's introducing a new object in the scene, basically. So what would be a correct way to do it? I'm going to propose another way to do it. So here's the original image with wool, right? The wool, right? For sewing, right? It's predicted as wool before. And then now if you erase this part of the image, then you introduce a new set of categories like with high confidence, actually. Home decor, person, cushion. Person, yeah, is predicted with pretty high confidence, which is kind of weird. So that also shows that black pixels are introducing information here. Now what you can do is do in-painting, right? Doing in-painting. So if you do in-painting, the hope is that you're removing the artifact introduced by the shape of the black pixels, right? Because you're now infilling with kind of pixel values that are kind of close to the surroundings, right? But we are not introducing extra information in this case because hopefully, right? It's not guaranteed because the in-painting is based on the surrounding context pixels, right? So it's just a guess of what should be there based on the information that's already in the input. Although, right? Although in-painting models, if you're using a parametric model for in-painting, then it probably has all kinds of information from the training set where that is trained. So it may still introduce new information, but at least from obviousness of the erasure, it's slightly better. In fact, you can kind of motivate this kind of missingness, addressing of the missingness as from a Bayesian, not Bayesian, just basic probabilistic theory of sum product rule. So the eventual quantity that you are interested in is what happens to the prediction of class C, given that you don't have information about pixel I, right? So we write x, the input, without the information about pixel I as x minus I, like this. And you can expand the expression here based on the on additional conditioning on the value of xi. Okay, so you're summing over possible values of xi, not xai, and you can do conditioning additionally on xi here, and then prediction of xi given x minus I. Okay, so now we can kind of see that c of x minus I and xi is exactly c given x, right? And now the p of xi given x minus I is an in-painting model. And you can replace this summation with some, you can do Monte Carlo estimation of this quantity basically. So you can do some sampling from the in-painting function, right? You can propose different possibilities to fill in those pixels based on the context. And for each simulated infilling, you can make the prediction for the whole model. And that's going to give you the estimation of the prediction when you erase the information in pixel I. So that's potentially one motivation to look into imputation or inpainting. These are the same words. And afterwards, when you have this value, then you can do some difference between the two values before and after the removal, or you can do log odds computation if you like. Yes.
I'm wondering why we like have to necessarily replace the pixels with other pixels. Not possible to like turn off the input neurons for those specific pixels that we want to ignore, and just use the information without like putting anything in replacement for those pixels.
Yeah. So yeah, it's not super clear how to do it, right? For sure, one method is to do in painting, right? But you're suggesting there may be some other possibilities. I show that, yeah, black pixels are probably not a good idea because that introduces new information. Do you have any other suggestion here?
I mean, like, why don't we just like not give any information for those pixels? Like, can we just sort of delete them, or like when we do dropout, I guess, just delete them from the architecture for those specific pixels.
Right, so you can do removal in the input space or in the intermediate feature space as well, right? For example, right?
Does that work, or?
So if you do it in the intermediate feature space, it's not super rigorous because the information gets mixed, right? Even from the first layer. So it's kind of difficult to segregate the information from that point on. In the inputs, again, erasing individual pixel values is potentially possible, right? You can just put some value there, right? But then the pattern of removal, right? Which pixels are being removed? That also kind of gives you a kind of a, remember this, the input is kind of a 2D space, like 2D array. So when you have certain shape along which the information is removed, that shape itself could be kind of an information for the model. Another possibility is to introduce a new pixel value that corresponds to no information, which is potentially outside the range between 0 to 255. Maybe that's the cleanest solution. But then the problem is usual models are not trained with this extra value. So if you want to explain existing models, then we still have to find another solution.
We're not just looking for something that is like theoretically sound as giving another solution, but also is appropriate for the given model.
Right, exactly, yeah. We have to kind of look into this very small intersection, yeah, between these criteria. Right, so that's it for the soundness, faithfulness evaluation for feature attribution. There's no easy solution actually for removing information. We just keep that in mind and still kind of use imperfect methodologies for evaluation. Okay. Now, I wish to briefly introduce one method for end-to-end evaluation, which is, I thought, quite fun. I just wrote down all kinds of end goals that you can have for feature attribution. It's boring, so I'll skip. So XA objectives beyond soundness, right? So eventually you have explanation, but based on the explanation, you have different end goals, right? So one example is debugging, right? For ML engineers, they want to take a look at the heat map in order to get an idea of how to improve the model later on. Scientists, they can train a model for kind of describing some observational data. And then from that, they try to understand what is the dynamical system, for example, or what is the underlying mechanism that is kind of potentially understandable to humans. For doctors, they want to gain more trust and reliability for the model. So eventually, they want to kind of get an assurance that they can use this model for their application. Now, so far, the focus of soundness has been more on the first side of things, right? Up until you generate this explanation. But now, in practice, when people get to use this, right, you may have different goals in mind, right? So in those cases, you have to measure the performance that is tied to the end users and so on. So I'll give you an example of how this could be done. Human in the loop evaluation. So we have two potential end goals here. So one is discovering potential bias in model for the model engineer to improve their model. And in the second case, we have a scientist, end user, who wants to understand how the model is making prediction whether this leaf is, yeah, whatever, right? This expert knowledge, right? And they want to use this for educational purpose, right? Training a new leaf expert or tree expert. Yeah, so evaluating explainability methods through end goals XAI. So now how do we measure whether these heat maps are helping helping end users with their goals? So to measure that, they come up with this framework of training a human evaluator. So they let a person sit in front of the monitor and give them a lot of samples of input, output, wolf, and the heat map. So k times, right? And then eventually what they are asked to do is, given a new image, you predict what the model is going to predict. Yeah? So if the heat maps have been kind of telling the evaluator a lot about what the model is actually doing, then maybe the evaluator has developed some kind of internal model for the model, right? Model of like theory of mind for the model. And then for the new situation, the evaluator will probably know what the model will do, right? That's exactly what, well, that could be one end goal of the XAI, right? Really understanding what the model is doing. So it's training a human instead of training a machine for the prediction task. So, but since, yeah, we need some reference points again, right? As we did for remove and predict. So we set the baseline as kind of showing still the input-output pairs from the model to the human evaluator, but not the score map, right? So how far can the model evaluator predict the prediction to the new sample, given that the evaluator has only seen input-output pairs? Yeah. So kind of comparing against that will tell us how much additional information these score maps will give, right, to the human subject. So we divide the values, and so if there's no additional information in the score map, then we'll see 1 or even less, right? If there's information, then we're going to see greater than 1 score for utility k, where k is the number of samples the evaluator has seen. And here's the results that this paper shows for this discovering bias task. The baseline is at 1, right? And x-axis is the number of training samples for the human evaluator, 5, 10, 15. And all these colors here, except for the dashed line here, is a XAI method, basically a score map generation system, right? For all of these score map generation, we see that even at very low number of training samples, the utility case statistically significantly greater than 1.0, meaning that there's information that is informative to the human subject, which is great. And that tends to increase with the number of training samples to humans. So that also aligns with our expectation. There's one exception, which is the saliency method, which is, I think, oh, okay, salience. So I thought that was input gradient, but since there's also input gradient, so saliency probably means model agnostic methodology. I don't know. So maybe you can check. It doesn't matter too much. The message is conveyed. Here, they also compare against the control case, which is they're showing some score map, but the score map is independent of the model, right? So the score map is, I thought that was saliency actually, because saliency also kind of means bottom-up indication of which pixels are probably most salient to human eyes. Like, so when there's a red part in the image, this is usually marked as salient. So there's a kind of a bottom-up way to kind of detect that, and you can use that as a potential score map, and that's independent of the model in question. So, and then if you look at this dashed line, then it's close to or lower than 1.0 utility K. So it's all as expected. Great. Now for leaves as well, we have the same conclusion. For most of the methods, we see utility K greater than 1.0. If you take a look at control, actually in this case it goes beyond 1.0, which is kind of funny, but still it's lower than in general than the other, other cases. Maybe just showing some score map helps human subjects learn better how the classes are. And quite importantly, they also measure the correlation between end-to-end usefulness as measured in utility K versus faithfulness based on remove and predict. So for each task, we have Husky, Leaves, and ImageNet, which I didn't really talk about. So they have 3 groups of points, circles, squares, and triangles. And then different colors are different score map generation. What they try to see was if a score map generation method is better in terms of end-to-end usefulness, does that mean that it also has better faithfulness or vice versa? Does better faithfulness mean better utility for end-to-end application? And they found that there's no strong correlation between the two. So that is a negative case against soundness faithfulness evaluation, actually, as a unit test for end-to-end applications. Yes? I don't know on top of my head, but my guess is that, as usual, they measure the remove and predict paradigm. Because they say it's deletion, and that to me means you're deleting according to the most important pixels as dictated by the score map. Okay, so let's go a bit more technical now and move into methods, feature attribution methods. Let's take a look at continuous inputs first. As I said, brute force computation is one sure way to get all these contributions, feature attributions, but it's expensive. How to make it more efficient, right, using input gradient. It's obvious, right? You can just take input gradient. But what I'm going to tell you here is what input gradient really means, again, right? So special case of like counterfactual reasoning is the features are individual pixels of the image, and more importantly, the perturbation has to be small, right? It has to be very local to the current image. So what you can do, for example, is you can pick a single pixel, and let's say the original pixel value was 232 and so on, and then you change a single value, like a single pixel value out of 255, then change it to 233. And then let's say the CAT score changes from 96.5 to 96.4, okay? Then that's exactly the amount of contribution that this small change is making. So dumb way to do all of this in all the pixels is to do that for number of pixels times 3 times, where 3 is because RGB channels, right? You have to do that 3 times for each pixel. And then you're going to get like pixel-wise contribution, of course. But that's too dumb, right? So a slightly smarter way is to do to remember that the definition of gradient is exactly these infinitesimal changes in the model output given the infinitesimal changes in the input for each pixel, right? And then and also remember that this computation is done pretty quickly nowadays with backpropagation with a deep learning framework, right? So what you do is you just do a backpropagation from the final prediction for cat all the way back to the input pixels, and that's it. So if you draw it schematically, right, you have an input here, and then you have a perturbation at pixel I. So EI is a one-up vector with 1 at pixel I, okay? And then you're introducing delta change there, right? Where delta is super small. So the difference in function output f of x plus delta EI minus f of x is approximated. It's a Taylor expansion, or it's just a definition of gradient as well, is the dot product between the delta EI vector times the gradient, the input gradient of f, right? Which can be written as delta times partial gradient of f with respect to xi, okay? So the point here is that you're now turning this function f into a linear function in the vicinity of x, test input x, right? So your f of y is exactly f of x plus y minus x times the inner product between y minus x and the gradient, right? So it's a linear function. And remember, linear function is an interpretable quantity, right? Although it has to be sparse. And if you ask if this is a sparse function, I don't think so, right? That's why people are complaining that input gradient is not really good, right? Because what you're going to see is something like this, and it's far from being sparse, right? You see a lot of noise here. Okay, anyways, this is what it is, right? What input gradient is telling you, how those infinitesimal changes will kind of change the output infinitesimally, whether that matters or not, right? I'm not sure if that really matters a lot in practice, whether those small changes are really important. I don't think it actually tells anything about the model, to share my personal opinion. So when people say they take a look at the input gradients, especially in this kind of image setting, then I say, you can do that, but I don't see the point. I don't see the point. It's not really telling you what you expect it to tell you. Anyways, from technical perspective, what people also do is, because if you get the input gradient, you have h times w, height and width, times 3, corresponding to channels. But to generate a heat map, you need to do 2 steps. One is to remove the channels, right? Because what we care about is the ranking of the pixels, right? So locations, ranking of the locations, rather than ranking also in terms of R, G, and B, right? So what people do is to take the max across the channel dimension and use that as kind of the signal for the importance of that pixel. And then this is mainly for visualization. You also want to kind of restrict the range of values here between 0 and 1, because that makes it nicer to visualize, right? I mean, if you do imshow, right, then it's internally probably doing that anyways for you. But if eventually what matters is the rank of the pixels within an image, then it doesn't matter whether you did this max normalization or not. Okay, so as I said, one of the many issues here is that it's way too noisy. So what people came up with is something called smoothgrad, which is computing the gradient at different perturbations of the input image. Yeah. So you perturb the input image with Gaussian noise a few times, and then for each of these cases, you compute the input gradient, and then you sum over all these input gradients. And that gives you slightly better results. But again, you should not rely on your kind of person, like human eyes, to tell if it's better or not, right? But anyways, it gives you more pleasant image. And people were happy with that in 2017. And this is how it looks like, right? So you have an input image, x, and then originally you just care about how x and x plus delta ei compares, right, in terms of the model outputs. But now you have multiple of these copies around the vicinity of x. So you can have x plus z1, x plus z3, and for each of these cases you compare against the z plus x plus z2 plus delta ei, right? So it's a little bit complicated, but this is what they do. And for each case, they compare these function outputs and then do the average over these function outputs. So Z is kind of the noise here, and yeah, the difference is kind of aggregated. And the aggregation and the taking the dot products can be swapped because both of them are linear. So what you can do is you just take the gradient on every location and then take the average of these. Yeah, I mentioned smooth grad, although I don't really like smooth grad so much because I feel like that's giving a nice kind of stepping stone to the next kind of method here, which is integrated gradient. Again, here the question is, why do you always have to kind of shift the input in the vicinity of the original input? Why can't you just maybe move a little bit further, right? So here, the idea is that you move the image from the current state, the test image from the current state, to all the way to something called baseline image. Typically, that's a black image. So you have a black image and you have input image, and you in the input space you draw a linear line between the two. So in practice, this will look like your image will be dimming all the way down to a black image. Yeah. And along this path, you compute the gradient and then average across this line. Yeah. So maybe that sounds a bit arbitrary, but there's a nice connection to what is called fundamental theorem of calculus, right, in multidimensional space. And this gives rise to a nice completeness axiom that I'm going to explain in the next slide. So again, what they do is they take the average across the line segment parameterized by alpha, right? So you're kind of taking random alpha value from 0 and 1. And then, so at every alpha, you're going to have kind of the reference point, x plus alpha times x prime minus x, where x prime is the baseline point, the black image. And then for every point, each one of these points, you take the gradients, basically, and then sum over these gradients. Okay, so why do you do that, right? There are some nice, yeah, so this is the formula that we derived, right? So for pixel I, the contribution of pixel I is defined by inner product between ei times the sum over the input gradients along this line. And what integrated gradient says we should be measuring on top is x prime I minus xi times this quantity. Okay, I'm going to explain why do we care about that. So now we have this kind of quantity x prime I minus xi times this, right? That's what integrated gradient should be computing. Let's say we sum this quantity over I for all pixels I, okay? Then we're going to have this summation over I. And then we realize, yeah, this summation and scalar multiplication can go inside the inner product because this is linear. And then if you do sum over x prime I minus xi times ei, that's exactly going to be x prime minus x as a vector, right? Right, because ei is a one-hot vector for each pixel I. Okay, and then you're assigning basically x prime I minus xi for each pixel, and then you kind of sum over these one-hot vectors, and then you're exactly going to recover x prime minus x. Yeah. So what does that quantity tell you? So if you remember this fundamental theorem of line integrals, it tells you that if you do integral over a and b for some gradient fields phi along this line, right? RT, right? T is the parameterization of this line, and you do you do the velocity kind of inner product, so you're always aligning the gradient to the direction of the line, and if you do the gradient summation along this line, then what you're eventually going to get is the difference in model values between phi of the endpoint and phi of the initial point. And now we plug in f into phi and the x plus alpha times x prime minus x as the line integral here. And then we exactly recover this quantity here. And if you remember correctly, so this quantity is equal to this quantity here, yeah? And then we see that it's actually equal to f of x prime minus f of x. Okay, why does that still matter, right? Because the initial starting point of our computation is summation over all the pixels, xi prime minus x, and then this quantity here, which is actually equal to f of x prime minus f of x. Okay, so if you rearrange everything, then what you get is an expression of f of x as some initial point f of x prime, the baseline point, plus summation over all pixels, where for all pixels you have some value to add, right? So it's now it's like it's again like a receipt that you get from a supermarket, where you have all these items, right? In this case, all the items are pixels, and you exactly know each pixel is contributing how much to the computation of current function value. So the difference between the function output for the current image and the black image is explained by individual pixel-wise contributions in this case. Whether that really tells you a lot about what each pixel is actually contributing, I can't tell, but at least in the final representation of the summation, it looks like a nice kind of summarization of how each pixel is contributing to the current prediction. So yeah, given this, people like to use this. And it's called completeness axiom, meaning that your final function is approximated by the summation over individual features. Okay. Right. So here's the result of that. So this is the original image, and the label is camera. And what integrated gradient is giving you is yeah. So as you see, you have to multiply with this pixel values in front, right? Xi prime minus xi, and xi prime is again a black pixel, so 0, right? So you're exactly multiplying with the pixel value in this case. And so you can think of the integrated gradient as kind of the integration of the gradient across all these line segments times the original image, multiplied pixel-wise. So you have this kind of image as the attribution map. And they argue, yeah, this looks much better than input gradient. Yeah, but again, this is kind of qualitative evaluation, so we don't really trust that so much. Here, one big caveat is that it depends a lot on what is the baseline image. Because let's say your image has black pixels, like here on the camera you have black pixels, right? And if your original image has black pixels, that pixel will have contribution 0 in any case, because this is multiplied in front, right? So I don't know if this is right or wrong, right? It gives you a nice formulation at the end of the day, but I don't think it makes total sense. But I still wanted to introduce this concept because, believe it or not, this is quite a popular approach still in feature attribution. Okay, so that was it for the continuous case, feature attribution. So I'll move on to discrete case unless there's any question. Okay. So discrete case, there are some advantages and disadvantages. Um, Disadvantage is that obviously gradient does not work anymore. For LLM attacks, we looked into how to make this possible still, right? You can also do token embeddings, right, and so on, and maybe it's possible to do it. But here I wish to introduce you more general framework than still rely on the gradient. Okay, so I'm going to talk about some methods here. But the other advantage is that if you move to discrete domains, the input dimensions tend to be smaller. So doing this kind of, so I criticize the brute force for being super computationally heavy, but maybe for discrete cases, it's not anymore the case, and maybe it's still feasible. And also in many cases, for discrete cases, actually there's sometimes a well-defined notion of no information in the input space. For some language models like BERT, you know what the BERT is trained for, right? It's trained to kind of fill in the masks in the input. And the way masks are, so it's trained by kind of leaving out some of the tokens from the input and then making the model predict that input. And the way you indicate where the model has to predict is by giving something called mask token for these inputs. So in this case, the BERT model actually has an inherent assignment of no information token in the list of vocabulary tokens. So for these kind of special cases, we can also use mask token for no information, which is great. But also for, in general, text, the sentence still kind of makes sense with the removal of some of the words, right? So without hurting the naturalness of the sentence. Of course, if you remove so many of them, then maybe it doesn't make sense anymore. But still, I would say no information still holds a lot better than in image domain, for example, in text domain. Also, these kind of language models tend to accept variable length inputs. So you don't have to really fill in some value for these cases, for the positions where information is removed. Okay, so I'm going to introduce a method called line in this case. So yeah, I'll get to the formulation, but before that, I'm going to give you some examples of how the computation is potentially done. So again, we are asking counterfactual questions to discrete data. We have some spam reply classification task, right? So it's a YouTube kind of comment, and we want to see which comments are kind of commercial and spam for everyone. So we should remove them, right? So first one is Sai is a good guy, and this is zero class, meaning that this is not a spam. And now we have for Christmas song, visit my channel. This is a spam because it's advertisement. So now for this particular case, for Christmas song, right? We want to understand which features are contributing the most to the prediction of spamness of the input. Is it for? Is it Christmas? Is it song? Visit my channel, and then this smiley face. Right. So for determining this, what you can do is to remove some of the tokens at random, right? So let's say the original spam likelihood is 99%, but if you remove 4, for example, then it drops to 94%. But now if you remove, for example, Christmas and channel together, then you get 70%, and so on. So there are so many like combinatorially many configurations you have here. And in each case, you can kind of record how much drop in likelihood you have, right? So these are the differences. Doing this is very reminiscent of what we did for input gradient, right? Because there we used to kind of erase each pixel, right? But in this case, we are removing certain token from the sequence and then see how the difference is for the the output of the function. Similar, right? Now you can also turn the original input into a sequence of ones, indicating that all the features are present. And then you can write down the other cases where you remove some of the tokens as zeros, right, in the sequence of ones. And so you have this representation here, Z prime representation, binarized input. And now it's conducive to kind of the approximation of a linear function, like fitting a linear function on top of these input-output pairs. So what we're going to do is, for this binarized input, we're going to fit a sparse linear model. The coefficients will be beta 1 up to beta d, where d is the length of the sequence. We're also going to introduce beta 0 for the case where everything is removed. Again here, okay. So eventually what we're going to get is a sequence, a set of equations. Like, for example, in the first case, we have beta 1 summed up to beta 7 equals to 0.99. And in this case, we have beta 2 up to beta 7, right? And so on. So we are going to have a whole set of equations to fit like this. And this is an over-defined set of linear equations. So there's no solution, of course. So you need to fit a linear regression here to accommodate some of the noises here. So it looks like this. So G beta is the linear model, and Z again is the binary input. And here indicates the index of different samples here, different rows. So you're trying to minimize the actual function output minus the difference between the actual function output and the predicted function output. Is exactly linear regression. But here we insert two extra stuff. So one is we value more the points that are not too different from the original input, okay? Which is regulated by WXZN, which is just measuring the distance between the perturbed sample and the original sample. By doing this, we focus more on the local vicinity of the test sample, okay? And that makes it a lot more like input gradient. Another factor is the sparsity constraint, lambda times beta L0 norm, where L0 norm is kind of computing the number of non-zero values in vector V, beta. You can, of course, relax this with lasso regression, L1 loss term, to have the same effect of sparsification of the betas. So after this, we're going to have G beta, which is the approximation of the original function f, around the test point of interest, Z, which is going to give you a sparse linear function, which is super nice for interpretation. I'm not sure if you have, okay. So I don't have the example for the previous example, but here's example output from diabetes versus no diabetes. And here are some of the potential factors like glucose, age, pregnancies, skin thickness, and so on. And then you can basically see how these different factors add up to the prediction of has diabetes. Okay, so it's a sparse linear function, so it's nice to look at. The question is whether this really faithfully represents the true cause. And for that, we need some faithfulness evaluation, of course. So that was it for the line part. Now let's take a look at the second method, Shapley values. So I would say LIME is kind of analogous to input gradients in the continuous domain. And now in the continuous domain, we also had integrated gradient, where we looked at the contribution of certain pixel along some global kind of change in the input. From the baseline all the way up to the current data point, right? Shapley values is a discrete analog of integrated gradients. And it also comes with nice theoretical results, saying like analogous to completeness axiom. Although that's my explanation, if you take a look at the explanation from other people or Shapley values in general, how it was conceived, you're gonna look at the history basically comes from econometrics, like economics, where people do collaborative work and there's a very complex structure how they contribute. And in this case, like if the contribution is a black box, right? Then how do you really assign the money, basically? Yeah. So you're co-founders and you're doing some work for the startup, and the question is how do you share the stocks, right? And for this, Shapley values is kind of a nice way to kind of determine who's important and how much share they have to eventually take. Because share is such a nice example of a linear function, right? They have to add up to 1, right? Or the number of shares, right, in the company. And so, however complex the situation is, they still have to come with a linear sum eventually to kind of conform to the legal requirement, right? Yeah, that's how it works. So again, so let's say the input in this case is gloomy, tense, yet profoundly inspiring. The prediction task is whether that's a positive comment or a negative comment. Yeah. So now the question is how much the word inspiring is contributing to the positivity of the sentence, for example. So this is again integrated gradient. So you move along the line x up to x prime, the baseline up to the current sample, and you take a look at how much difference there is, right? How much difference in outputs each perturbation is going to make, and sum over these, right? How do you discretize this, right? So you have now the original sentence x, and you were wondering about inspiring, the word inspiring, right? So what you're going to do is you're going to remove inspiring from the original sentence here, from x. Let's say that's I, token I. And then let's say the baseline is the case where you only have that token, just inspiring. And then there again, you're going to remove that inspiring token from the sentence. And then you're going to have an empty sequence, right? Yeah, that's still potentially valid input. The caveat here is that there's no linear segment connecting the current input all the way down to an empty set. There's no single path in this case. In the continuous domain, in vector space, there's notion of line, right? But in discrete space, there's no notion of line. So what you do is you take all possible pathways all the way down to empty set, which is to say you consider all subsets of the feature selections of the original input. Yeah, so what you do is you take the difference in function outputs between fz and fz minus I, where z is different subsets of x, the original input, but z has to contain the feature of interest, I. Okay, so that's what this notation means, right? So I is always included in z, but z is a subset of x. Okay. Right, and that's exactly what Shapley value means. So it's kind of integrated gradient as well. So the expectation here, it's not super clear how to weight different sizes of z, right? Because again, this is not a single line, so it's a subset. So if you take a look at different possible subsets for a huge list of features, right? Let's say there are 10 features, and you have to kind of, you look at the subsets of size 5. Then there are like 10 choose 5 different ways of forming the subset, and that's a big number. And that potentially makes it it a bit unfair in terms of how much weight different sizes of subsets have in the summation here. So what they consider is to kind of make the contribution of different subsets, different sizes, uniform. So you first do Shapley values for subsets of size 1, and then 2, and then 3. And then you take unweighted average of these sizes eventually. Okay. So in practice, what you do is you first sample subset size m from uniform distribution of the possible sizes. And then for each size, you do sampling of subsets, and then they do this difference computation. Right. I don't remember what I wrote here, since I is already chosen. Okay. You're just doing uniform subsampling of the subsets here. And the number of possible ways to get a subset here is size of x minus 1, choose n minus 1, because there's constraint that the subset has to contain I. Okay. And if you write it down, it looks like this. So you sum over different z, and then you do, so each probability for choosing a subset here is x minus 1, choose z minus 1. So you normalize by this count here. And that's exactly the likelihood of each case. And then you're dividing through by 1 over size of x. Yeah, here what's important is that eventually we're going to prove something like completeness axiom, right? They all have to sum to the original value of the function. And for that, all these constants matter. In practice, when you just care about the ranking of pixels or ranking of features, these constants don't matter so much, right? But for the sake of theory, it matters to kind of divide by this value. Okay. So that's it for the computation of Shapley values, actually. There are libraries to download to implement this. So now let's take a look at the importance of inspiring in the sentence. You have all different subsets of individual original token sequence containing inspiring still, and you have different positivity predictions, and you also have a set of predictions where you just remove inspiring from the cases on the left side. And then eventually you have on average 71% for the cases where inspiring is contained, whereas you have 21% for the cases where you don't have inspiring in the comment. And the difference here is exactly the quantity that we are looking for. Okay. Yeah, what's important here is to note that they actually satisfy the completeness axiom as well. If you sum over the values here, the contribution of each I, then it actually returns f of x minus f of 0, which has a similar formulation as before, where phi of fx actually correspond to this quantity here for the integrated gradient. Okay. Oh, yeah, that was it actually for the lecture. Yeah, I think I'm missing some conclusion slides here, so I'll make some conclusion. I think I deleted it by mistake this morning. So in both continuous domain, input domain, and discrete input domain, there are two extremes. So one extreme is you only care about the local kind of vicinity of the test input. The other extreme is where you also want to consider you're linearizing a function, yeah? And now the linearization is happening either only around the test point of interest, or the linearization is happening still around the test point of interest, but also kind of considering all the baseline points, right? Or the space in between. So if you're doing linearization around the test point, then I mean, this is linear, so this is still within the human interpretable kind of domain. But as soon as you move out of that domain, then you're kind of losing faithfulness of the approximation, which is not good. Whereas if you have more global definition of approximation of the function, then you're actually covering slightly more space, yeah, than just the local vicinity. In that sense, one may argue that this is reflecting the original function more closely, which is the nice advantage of this approach. But then still the caveat is how to define the baseline, right? For images in particular, it's not super clear whether black images are still the right kind of baseline to look at. Yeah, so because as you've seen, like letting some of the values take some baseline take some value in the input space. That means if the original input had that value in the input space, then that will basically be considered as no information, and it does not contribute to the final prediction of the model. So yeah, I just wanted to cover these pros and cons for each approach. Yeah, and next time we will continue with the second part of feature attribution regarding the methodologies where you actually do linearization of the function still, but you're linearizing the function for the overall input space, but only for a part of the model, like class activation mapping, if you know what this is. So it only works for deep neural network. So the first part of the network will still be considered a non-linear function, but you're only interpreting the last linear part of the model. And by doing this, you can still approximate the original function with a linear function over the entire input space. So there again, the advantage is that you're approximating the original function with a linear function over the whole input space. But again, you have to kind of give up on the first part of the network, which is doing a whole bunch of computation to kind of make the linear function kind of work at the end of this, right? So there is always this trade-off. Yeah, you eventually in feature attribution, you want to make some part of the function linear, right? But you have to kind of decide on where you're going to still keep the nonlinearity in, right? And which part you're going to make linear. And there's no way you can make everything linear, because once you make everything linear, then you don't have the original function anymore.